Here's a series circuit, and our job is to find the potential difference across each of those resistors. How do we know it's a series circuit? Well, we know that there's nowhere else for the current to go. It goes round in a one loop. There's no branches, it's just the one loop. So it's a series circuit. And that means the resistors are connected in series, even though that 2 ohm one looks above the 3 ohms and 5 ohms. But if you trace it through, all the resistors come one after the other, and it's a series circuit. So our first step to find the potential difference across each resistor is to find the total current flowing the resistor. And to do that, we can use Ohm's law. I equals V divided by the total resistance RT. Now we know for a series circuit, the total resistance is just simply the sum of all the resistances in a circuit, R1, R2 plus R3. So that's going to give us 2 ohms plus 5 ohms plus 3 ohms. So the total resistance of the circuit is in fact 10 ohms. And now we've got the total resistance, we can go ahead and find the current in the circuit. I equals the V, which is 1.5 volts, the voltage of the cell or the source, divided by 10 ohms. And that's going to give us a current of 0.15 amps. Now we know the current flowing through the circuit, then we can tell the potential difference across each resistor, because all we have to do is use V equals IR. So in this first one here, we can put down all the data which is associated with that resistor. We're after V. We know the current is going to be 0.15 amps, and we know the resistance is going to be 3 ohms. So therefore V is a simple case of saying V equals IR, which is going to equal to the current 0.15 times 3 ohms, and that's going to give us a value of 0.45 volts. So we know across this resistor you're going to have 0.45 volts. The same with the 5 ohm resistor. We put down below it all the possible variables. We don't know the voltage, we're trying to find that, it's a potential difference. We know the current, it's a series circuit, so it's got to be the same current, 0.15 amps, and we know the resistance is 5 ohms. So we do the same thing again, V equals IR, and that gives us a potential difference across that resistor, 0.15 multiplied by 5, and that's going to give us a total of 0.75 volts. So we know across that resistor is 0.75 volts. What about the 2 ohm resistor up here? Well, we do the same thing again. We put down V, I and R, and we know the current is the same, 0.15 amps. We know the resistance is 2 ohms, so therefore V multiply V equal to IR, we get 2 times 0.15, which is 0.30 volts. So therefore we've found all the potential difference across the resistor, and the important thing to note is that if you add up all the potential differences across each resistor, 0.3 volts, 0.75 volts, 0.45 volts, you will get the value of 1.5 volts. That's how easy it is to work these circuits. We can go back and take a look at the PHET simulation of that circuit to see if we are correct. And there it is there. You can see that we've got the 3 ohm, the 5 ohm, the 2 ohm, and we've worked out the correct current, 0.15 amps. If I take the voltmeter and go across the 3 ohm resistor, you can see we're going to have a potential difference of 0.45 volts. If we go across the 5 ohm resistor, you can see that we're going to have a potential difference of 0.75 volts. And finally, across the top resistor, we have to make sure the plus is connected to that side and that there, and that gives us 0.3 volts. So once again, all the voltages add up to give us 1.5 volts. We're becoming experts in series circuits.